So welcome everyone to this new OpenGl ES video. In this video, I will show how we draw a sphere in OpenGL in two methods. The first method uses the icosahedral. In this method, we will start by a polyhedral, as you can see in this figure here, which has 20 faces, and the vertices of these faces, these vertices here, are taken to be on a sphere. As you can see, this polyhedral does not represent a sphere very well since it's only using 20 faces. That's why we will go further and subdivide each face into 4 other faces, as you can see here. So we take the middle point of the 3 vertices of each face, and then we can create 1, 2, 3, and 4 triangles. And we will do that for all the faces, and the same can be repeated now for on the smaller faces. So we can imagine that we can go another step here and subdivide this face similarly here and here and so on. By repeating this division, we can reach a shape which looks very similar to a sphere. I will show later when we go into the code problem, when we try to texture a sphere which is created in such a way. There are some solutions for that. However, I will not be going through the solutions. I would rather show the second way, which is the spherical coordinates, and then maybe later in a next video we can see how to solve problem of the icosahedral, and maybe in a future video I can show how we can use a feature of OpenGL called cube maps to solve this problem. But let me now focus on the second way of creating a sphere, and in this way we'll be using the spherical coordinate system. Here we will be dividing the sphere similar to the longitude and latitude. So these would be the longitudinal lines and those are the latitude lines. So you can imagine here if we have a spherical coordinate system where we have for each point we have the angle theta between the x-axis and the current, and the projection of the current point on the xy plane. So let's say that we have a point here, so this is the projection of this point in the xy plane, and then we have also the angle phi, which represents the angle between the line connecting the point to the origin and the z-axis. In our case in OpenGL, this would be the y-axis actually, and this would be the x-axis, and this here would be the z-axis. And we will generate vertices corresponding to the intersection between these lines, as you can see here, and then we will take the neighboring 4 vertices here and make true triangles for each 4 vertices. And in this way we can represent the sphere, and if we want the sphere to be finer, we can have a finer division on the longitude and latitude. So let's start coding. Let's start creating this sphere vert class as we did for the cube. This class will create the vertices of the sphere using the icosahedral. That's the polyhedral with 20 faces. Let me paste the code of this class. I already prepared it. I use here a tag for debugging purposes. For creating the icosahedral, I have added this static code here. In this static code, we first create the vertices of this icosahedral. So those are 12 vertices, and then the 20 faces, so the 20 triangles of this icosahedral. Then I also created this class here, so static class. It means that although it's included inside this sphere vert, it does not use any member variables of this sphere vert class, so it's independent of sphere vert. This class wraps a hash map which has a string as a key and integer as a value. The integer value refers to the indices of the vertices which we start with or we add later. As you can see, this class also have a static function called key, which take 2 indices and just join them by a string and return it, and this will be using as a key. Later you will see that we want to keep track of the vertices when we create them, so we don't create the same vertex twice, and that's the main purpose of this map class. So we will save the indices of the 2 vertices, and the new value inserted here would be the vertex which in the middle of these 2 vertices. The insert function simply looks how we inserted this key. If yes, it returns false, so no insert has been done. If not, it inserts the key and the value and then return true. That means we inserted a new vertex. And of course there's this function get, which will return the integer value corresponding to the given string key. That's very straightforward. Let me start first from the constructor of this sphere vert. First, in the constructor, we create a list of vertices. This list will hold float arrays. These float arrays will contain the x, y, and z coordinates of the vertices. Then we also create a list to save the triangles. We will be saving the triangle as indices, so each triangle will contain an array of 3 indices. Those indices will refer to the location of the vertex in the vertices buffer. The first step, as you can see here, I'm simply looping through the start vertices, the static variable, and adding them to this vertex buffer, and then looping through the triangles, the start triangles, and adding them to the triangle buffer. After this step, we will not be using these static variables. All new vertices and triangles will be added in these two member variables. Then the final step in the constructor is to divide this icosahedral depending on the input number here. So let's go to this function divide. So in this function divide, as you can see, first we create an instance of this map variable, because we will be now creating a new vertices and have to track them. We also create a result here, which is a list of integers. So for every triangle which we subdivide, this list will hold 4 new triangles, as I explained in the introduction. So now here we loop through the triangle. So for example, at the beginning, so in the first subdivision, we have 20 triangles, and then this t will loop through them. And then for each one of these triangles, we initialize this mid variable. This mid variable will contain the indices of the middle point of the 3 edges of this triangle. So as you can see here, we loop through the edges, and for each edge we call this function get vertex index. This function will take care of creating the new midpoint, and for that it needs the map of the available points, so we don't create the same midpoint twice, and it needs the index of the first point in the edge from one end, and the index of the point on the second end of the edge, the end of the edge, if you like. And as you can see here, I'm taking mod 3, so that means in first we will compute the midpoint between the first and second vertex of the triangle, then between the second and third, and then between the third and the first one. So here first one means the vertex at the null index. Let's take a look at the function get vertex index. So this function first sort these first and second index. So now first will contain always the largest index. This is done because it doesn't matter at which triangle edge we start. The midpoint would be the same, so we don't need to create it twice. Then we can create a key based on these two indices and call the function insert. So now if this vertex is already inserted, this inserted will be false. Then we don't add a new vertex here. However, if this vertex was not available in the map and we have inserted it, then we need to create a new vertex. For that, as you can see here, we take the first end, the second end, and we add them. This add function will simply add these two float arrays and return the result. Then we compute the norm of this and we scale by the norm. I think this can be replaced by the function called normalize. So we already have a normalize function which take a float array and normalize it. Those functions in the math utils, we already went through them in a previous tutorial, and this normalization is done because we are assuming now that the radius of the sphere is 1, and by normalizing we are ensuring that any point which we create is on the surface of a sphere which has a radius of 1. Finally, we add this new vertex and we return the key. That's it for this step here for getting the index of the new midpoints of the edges. Now we have the 3 new midpoints. We can create the new 4 triangles as explained in the introduction. So we only need to add the indices, and we will always have 2 indices of the midpoint and 1 of the original triangle points, and 1 triangle will contain only the 3 new midpoints. And that's it. Now we have 4 new triangles. We add them to this list, to the result list, and we return it. That's it. So now we can do as much divisions as we want, and we can make this sphere finer. Now we have created this triangle using indices of the vertices in the vertex buffer. We cannot use them directly in our objects pObj or bctObj because these two objects which we create earlier expect the coordinates of the vertices and not the index. In OpenGL, there is a way to also create triangle using indices, but I will not be using that here now. So to make this code now compatible with the pObj and bctObj, I created this function getPositions, which simply will loop through the triangles, and for each triangle will get the vertices and add them to a buffer and return this buffer. As you can see, this buffer size will be the number of vertices per triangle, which is 3, multiplied by the number of floats per vertex, which is also 3, and then multiply it by the number of triangles. Of course, there is redundancy here since we are writing each vertex 3 times, but that's a kind of optimization which I don't want to go through in this tutorial. So that's it for this function getPositions. I also created a function called getPositions and texture. This function will take the positions as before and add them to a buffer. However, it will also look at the texture corresponding to each vertex and also add it to the buffer so that we can use the result here in a BCT object. So if we want to texture our sphere, then we should call this function here. The function onTriangleTexture simply takes the 3 indices of the vertices of the triangle and will return 3 coordinates uv, and that's done for each vertex by itself. We simply take the vertex and normalize it to get the radius. This could be redundant because we will start always by radius 1. Then we will compute the latitudinal and longitudinal coordinates. Then we will compute 2 angles. So for each vertex, we convert it from Euclidean coordinates to spherical coordinates. So we compute the rho, theta, and phi. And we will simply use the theta and phi to compute the corresponding texture. So we simply need to map these theta and phi between 0 and 1. So this function wrap to 2 pi wraps the values of the angles between 0 and 2 pi. However, this angle phi will be always between 0 and pi. So for each vertex, we compute the spherical coordinates rho, theta, and phi. Then we will use these 2 angles, theta and phi, to compute our coordinates u and v. So first we wrap these 2 angles between 0 and 2 pi. This function is simple. It just looks if the given angle is larger than 2p, then it subtracts 2p. And if it's smaller than 0, it adds 2p. Then the resulting value v here would be between 0 and 2p. It's important to note here also that phi will actually be between 0 and p since we are using this arc cosine function from Java. So to normalize these 2 angles between 0 and 1, we need to divide theta by 2p and phi only by p. And then we save these 2 coordinates and we go through the second, and then we can return these 2 coordinates, and that's it. So this is all about our sphere vert class. Let's use it in our main activity. So I already prepared a code. So as you can see, we create an instance of this class spherevert, and we use the function getPositions to create a pObj class since we only now getting the positions, and we pass the color. Then we add the sphere to the scene. Let me comment the previous code here and run the application. So as you can see, we have now a sphere which is not very fine since we put these subdivisions here to 0. We can make it larger. So it's much better as you can see here. And of course, we can add rotation around the y-axis. So and that's it. Let me, however, make this even finer, this subdivision, maybe 5. And it looks now very fine. However, we don't get the 3D feeling because we don't have material or light implemented. Maybe we'll be doing that in next tutorials. However, in the next example, I will add a texture to this sphere, and that will give us a better 3D feeling. For now, we can add a wire object to it as we did for the cube. So let me copy this code here. And let me put this as vert. And we need to match the angle, and that's it. That looks weird because we got our stride here wrong. So we only have positions, we don't have texture. Now let's rerun. You can see now how fine the divisions are. So let me lower this down. Of course, you can play with this. So take your time, play with these numbers and how quickly this surface will be fine by changing this number here. However, don't use very large numbers like 100 or so, because then you will be creating too many vertices. Now let us add a texture to this sphere. I already prepared here an image of the Earth and will use this image on the sphere. So now instead of using getPositions, we use position and texture. And of course, here in the stride and the wireframe, we want to use again the float sphere texture. As an object, we want to use the BCT obj. Since now we have texture, so this needs the vertices. The boolean has color, that would be false, and has texture would be true. And then the path of the image, which is images earth. Let's run now. So as you can see, we got the texture. Let me zoom out a little bit to see the problem here. Now we have a problem in this side here. Let me make the rotation slower. So I stopped the rotation so that you can see the problem here. So you can see for some triangles, the texture is computed wrongly. To explain that, I already prepared this image here. So we have our texture, which starts by 0 on the u coordinate and end up by 1 here. So this is the direction of the u coordinates of the texture. And we use the angle theta. Let's say that here is the 0 axis for this angle theta, and the angle increases in this direction. So it will be maybe here 45, then 90, then 180, and then it comes back here at 360. So the problem here is when we have a triangle like this, which has vertices with an angle theta, which is very small, maybe 20 here, 20 degrees, and some vertices which has an angle which is very large, such as 300 degrees, for example. Now for computing the color of the fragments of this triangle here, OpenGL will interpolate the coordinates, and it does not know that it should go in this direction here. Basically that the image folds on itself. That's why it goes in this direction and we get a wrong texture. You can see that this effect will become less observable when we have higher division. So let's say maybe 3. You can see now the triangles are smaller, and the ones which are here, only the ones here are getting the wrong texture, and so on. Maybe if we turned off the wire object, now you can see it's really small. To solve this problem, we have to go to cube textures. However, I will not be doing that in this tutorial. Instead of that, I will try to create the vertices of the sphere so that we have a clear cut here at this line. So none of the triangle will be like this one. So all the triangle will have vertices either at this side of this line or from the other side. And that will solve the problem, as we will see. So for that, I have prepared another vert class. Let me copy that. So this class, I called it sphere vert2. And yeah, I started with this static definition of P. So I don't want to cast P every time from double to float. Also define this static class, vertex data, VD. This class will contain X, Y, Z, U and V, which are the coordinates of the texture, and alpha and beta. So those are the angles theta and phi from the previous class sphere vert2. Let me maybe refactor this to theta and phi. ing would be integer counter corresponding to the angles theta and phi, and this variable index will be the index of the vertex in the vertex buffer. So this class has one static function called from grad, which takes two indices, ing. You can think of I as counting from 0 to gradation, and it represents the angle theta, and G also counts from 0 to gradation. However, this will be for the angle phi, and we also take the radius here. So as you can see, this function starts by creating an instance of red and saving the indices ing, then creating the theta and phi corresponding to the indices ing. So this is simply I divided by gradation multiplied by pi for theta, and I divided by gradation multiplied by 2 pi for phi. So I mixed up the names here. So this actually should be theta. So this should be phi, and this angle here should be theta. Having computed the phi and theta angle, we also have the radius here, so we can compute the x, y, and z coordinates corresponding to this point. And finally, same as before, we want to compute the u and v coordinates. This is the same as before, and we can now return this instance of the VD class. That's it. And now let's go to the class sphere vert2. As you can see, it has, as before, a list of vertices, and now this list is from type VD. And the list of triangles, which the same as before, it's an integer array. The constructor of this class requires the radius and the gradation. So basically how fine we want our sphere, and then it create these two array lists and call this function create with one texture. So this function will simply create two rows of vertices. These two rows, we can imagine them as two circles corresponding to two different values of the angle phi. Actually, it's called here alpha, but it's also not used since all is done in the function vd dot from grad. So this function will create two lists of vertices of type vd. They are called previous and current, and then draw the rectangles by connecting the vertices between these two lists. We will be taking the previous to be the current at the end of the loop. So here we only need to initialize the previous list. And in the case where g is equal to 0, we only create one vertex inside this list previous, and that would be representing a point at the bottom of the sphere. Then we go through this loop where we will be creating a number of vertices equal to gradation and adding them to current, and then calling this function connect. There is also another special case when g is equal to gradation here. We also create only one point in the current list, and that would be corresponding to the top of the sphere or the north pole, if you like. And that's it for this function. So we only now need to look inside add vd, which is very simple. It calls the function vd.fromGrad and put the index to the size of the vertices and then add it to the buffer. And the function connect is a little bit more involved. So it will take the list of these two vertices, and now there are two special cases. So if the previous list has only one vertex, then we will connect this vertex with triangles to all other vertices inside the current list, and vice versa here. In any other case, the number of vertices inside the prev and current lists will be the same. So we loop through them. We start from 1 going to the size, and each time we take the vertex from the list previous, which is at the position i-1, and the vertex from previous at the current index I. The same here for the current, so one from I, the one from I-1, and now we have 4 vertices which make a rectangle. Then, as we did before, so for a rectangle we need to create 2 triangles, as you can see here, and add them to the list of triangles, and that's it. So we already now have created our mesh. Same as in the previous class, we have here a function to get the position and the texture, and this function also similar to the previous one. We just loop through the triangles. However, here it's simpler since we only need to collect the vertices and the coordinates. We don't need to recompute the u and v coordinates. And that's it. Let's try this class now. Now, instead of using spherevert, we use spherevert2, and let's give it a radius of 0.5. And let's start by a gradation of 2, and let's run. So you can see if we only have 2 gradations, then we will have 4 vertices, one in the north, one in the south, and one to the right, one to the left. Maybe we should rotate this sphere so you can see that. So it's a good idea to create more gradation. Let me put it to 5. And now you see that the point in the pole is connected to all the points in the circle below it, and the same here. It's also a good idea now to put the wireframe back and rotate it with the same angle. So you can see what's happening. So we already made these rectangles, and each rectangle consists of 2 triangles. And that's it here. We can have a final gradation. And you can see that we don't have the previous problem. And that's it for this video. If you like it, please give it a thumb up and subscribe the channel so that I can add more videos like it. Thanks, and see you in the next video.